If you're not an engineer, you might think the most innovative advancements in tech are found in our devices, vehicles, and machines. The delicate circuitry and mechanisms under the hood, right? But what about the hood itself? The outer armor that protects the delicate stuff inside. Like the shell of a rocket, under the crushing stress of its massive thrusters pushing up against its own massive weight. For John Hutchinson, innovation doesn't just push boundaries, it makes them stronger.
I thought of myself, until I went to college, as being very American, even though my father was Irish and had a bit of an Irish accent.
Growing up in Bridgeton, New Jersey, Hutchinson came of age at an anxious time for the U.S.
Sputnik caused me to switch my major at the end of my sophomore year into an engineering mechanics department, which, as far as I could see, was much more closely related to space.
The U.S. was leaving Earth, and leaving Earth is hard work. Rockets had to remain lightweight while managing to withstand the tremendous stresses of liftoff. Like most engineers, Hutchinson, then a researcher at Harvard, thought this was a challenge of form, of the shape of the rocket shell.
Shell structures can be incredibly strong while remaining very thin. These eggshells, for example, can support the weight of 10 bricks.
Sadly, chickens don't lay rocket-shaped eggs, so engineers relied on mathematical models to find just the right shape for a rocket shell. Those models predicted stability, durability, and success. And yet, at the dawn of the Apollo era, U.S. rockets were failing at just 20% of the predicted stress thresholds. Engineers ran exhaustive tests.
Pretend this soda can is a rocket cylinder. If we could predict where it's likely to buckle during liftoff, we could reinforce just that spot, minimizing the weight. The problem is, we can't predict where buckling occurs at all. Even with lots of repeat testing, the location of buckling is wildly inconsistent. The same holds true for rockets.
Perplexed engineers resorted to making early rockets thicker and much heavier, reducing carrying capacity. But Hutchinson wasn't so quick to give up. If thinner, lighter shells were buckling, there had to be a reason.
Yes, failure is very interesting. You have to understand it. You have to be able to characterize it.
Hutchinson reasoned that there was nothing wrong with the mathematical models used to design rocket shells, that the unpredictability lay with microscopic material imperfections introduced during manufacturing processes. The resulting flaws in the arrangement of molecular building blocks would cause sections to slip out of place, like misaligned bricks in a wall. This shift in perspective changed everything. Hutchinson began making himself an expert in the physics of manufacturing methods and how microscopic material grains are affected by shaping processes like deformation and solidification. Eventually, Hutchinson devised groundbreaking computer simulations that could pinpoint where consequential material imperfections were likely to occur. For the first time ever, engineers could predict where shell structures like rockets were likely to buckle and could use targeted reinforcement in their designs.
It was a small team at Boeing who really first began implementing. So that summer, I actually was involved in helping them calculate wing stresses for the B-52.
It wasn't long before NASA took notice. Hutchinson's simulations greatly increased the weight capacity of satellites and other spacecraft, transforming rocketry and history in the process. As he expanded his groundbreaking simulations, his insights directly contributed to safer, stronger airplane fuselages, accelerated the development of cutting-edge fuel tanks, and enabled revolutionary high-pressure storage containers. Thanks to Hutchinson, we are pushing boundaries beneath the ocean, beyond the atmosphere, and into the tiniest technologies, breaking open a future of enormous possibility.